Okay, so we are almost done. So we've shown that 1 over x squared is continuous on this open interval from 0 to infinity. And we've shown that 1 over x squared is not uniformly continuous on that open set. The last thing I wanted to do is give you an example where we're proving that 1 over x squared is uniformly continuous on this set right here. So notice that we already proved the theorem which says you can conclude that f is uniformly continuous on a closed interval as long as it's continuous, right, on that closed interval. Now we're going to look at an example that shows f can be uniformly continuous on a set that's not closed and bounded, okay? So let's go ahead and look at this. So where are we focused? We're focused on this example right here, example 2. So we're trying to prove that a is fixed, a is positive. We want to know why is it that f of x equals 1 over x squared is uniformly continuous on this unbounded set. So let's go back to the definition. The definition says that f will be uniformly continuous on that set if and only if, for every epsilon greater than 0, there exists a delta greater than 0, such that for all x, y, whenever the distance between x and y is less than delta, the distance between f of x and f of y is less than epsilon. So now I just did an if and only if to rewrite what does it mean to say x and y belong to this set. Well, that just means that x and y are bigger than or equal to a. And then what does it mean to say that the distance between f of x and f of y is less than epsilon? And that just means that the distance between 1 over x squared and 1 over y squared is less than epsilon, because the function that we're looking at is given by the formula 1 over x squared. Okay, so my goal is to show that it's to find a delta where whenever x and y are bigger than or equal to a, if this is true, then this is true. So I'm ultimately wanting this to be less than epsilon. The thing I have to work with is the distance between x and y is going to be less than delta, and I get to choose delta. And I also know that x and y are going to be bigger than or equal to a. Okay, so again, I just am rewriting, and I want this to be less than epsilon. So I want this to be really, really small. That's the idea. And I'm looking at it, and I'm going to factor this. First, I can rewrite the numerator as the distance between y and x times the absolute value of y plus x. And then the denominator, I can just have x squared, y squared, right? Absolute value there. Now notice that since a is bigger than 0, and x and y are bigger than or equal to a, I actually can remove the absolute values here. And I also can remove the absolute values from the x plus y, because x plus y is going to be positive. So I'm trying to get this to be small. And I know that this, I can make this less than delta. So I want delta times x plus y over x squared, y squared. How can I get that to be less than epsilon? What does delta need to be? Right? Like, what kind of delta makes all of this less than epsilon? Okay? And delta can't depend on x and y. Because otherwise, I would just say, oh, well, let delta be, right? But no, I have to give a delta that doesn't depend on x and y. Okay, so here's where we're going to do our estimation. I'm going to rewrite this as x over x squared, y squared, plus y over x squared, y squared. And then I'm going to do some canceling, so I'll have 1 over x, y squared. And here I'll have 1 over x squared, y. Yeah? I'm looking here, and I'm trying to get all of this to be less than epsilon. And I know that x and y are at least a. So if x is bigger than or equal to a, then that means that 1 over x has to be smaller than, right? X bigger than a implies 1 over x is going to be smaller than 1 over a. This and a bigger than 0. And the same thing is going to be true for y. So I'll actually have 1 over x y squared is going to be less than 1 over a cubed. And also 1 over x squared y is going to be less than 1 over a cubed. So delta times 1 over x y squared plus 1 over x squared y is always going to be less than or equal to delta times 1 over a cubed plus 1 over a cubed, which is delta times 2 over a cubed. So now I want this to be less than epsilon. I know that this is always less than or equal to this. So if I just make this less than epsilon over delta, then we're good. Does that make sense? Because then delta times that will be less than epsilon. So to get that to be less than epsilon, I should say, oh, okay, well, delta needs to be less than epsilon times a cubed over 2. So I figured out which delta works. So here's my scratch work. And I'm going to say, aha. So and maybe we do a new sheet of paper here to make it clean. For epsilon greater than 0, let delta equal epsilon times a cubed over 2. Then, whenever this is less than delta, that implies y squared minus x squared over xy. Wait, what was it? Over x squared y squared. So this is going to be equal to y squared minus x squared over x squared y squared, which is equal to y minus x times x plus y over x squared y squared, which is equal to this times 1 over x y squared plus 1 over x squared y, which is less than, right, so this part is less than delta, but delta is this. This is going to be less than epsilon times a cubed over 2 times 1 over xy squared plus 1 over x squared y, right, which is going to be less than or equal to epsilon times a cubed over 2 times 1 over a cubed times 1 over a cubed, which is equal to epsilon. So I get this less than this, as desired. Okay? So we've shown that 1 over x squared is uniformly continuous on this domain, even though this domain is not bounded, right? And we have the theorem that says if you have a function that's continuous on a closed and bounded interval, so closed and bounded interval, then f is uniformly continuous. Okay? All right, that's it.